In this video, we're going to be talking about the definite integral. Now, in the previous section, we only considered functions that are positive or above the x-axis. In this section, we'll look at a more general case. First, let's give a special name and notation to the work we did from the previous section. If f is a function defined for x being greater than or equal to a and less than or equal to b, we divide the closed interval from a to b, into n subintervals of equal width delta x, which is equal to b minus a over n. We let x sub 0, which is the same thing as a, x sub 1, x sub 2, all the way to x sub n, which is also equal to b, be the endpoints of these subintervals, and we let x sub 1 star, x sub 2 star, all the way to x sub n star, be any sample points in these subintervals. So x sub I star lies in the ith subinterval, which has endpoints x sub I minus 1 and x sub I. Then, the definite integral of f from a to b is given with this notation, and it's equal to the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I star times delta x, provided that this limit exists and gives us the same value for all possible choices of sample points. If the limit does exist, we say that f is integrable on the closed interval from a to b. So let's clarify the names of some things. So in our previous definition, we saw this symbol here, and if it looks like an elongated S to you, that's actually purposeful, and it's meant to look like an S because an integral, or a definite integral, is essentially a sum, and summation starts with S, so that is why the integral symbol looks like that. It was introduced by Leibniz. F of x, or the function that we're integrating, is called the integrand, and a and b are called the limits of integration. A is called the lower limit of integration, and b is called the upper limit of integration. The procedure of calculating an integral is called integration, and this summation here is called a Riemann sum. Now, a definite integral can be interpreted as a net area, that is, a difference of areas. So when we were looking at a function that was above the x-axis, then the definite integral is equal to the area between the curve and the x-axis. But if we're now looking at a function that's not always positive, that means that sometimes it falls underneath the x-axis. Anywhere the function is above the x-axis, we are summing those areas, and then any of the function that falls below the x-axis, we're also summing those areas and then subtracting them off. And so this figure 3 here is representing a Riemann sum, and then figure 4 is the exact net area modeled by this definite integral from a to b of our function f of x dx. Keep in mind that not all functions are integrable, like sine of 1 over x, but commonly occurring functions are, and those are the ones that we're going to focus on for the most part. Our next theorem says if f is continuous on the closed interval from a to b, or if f has only a finite number of jump discontinuities, then f is integrable on the closed interval from a to b. In other words, the definite integral from a to b of f of x dx exists. Now, this is where differential and integral calculus differ a little bit. In your previous math class, you might have encountered that when you're taking the derivative of a function, in order to take the derivative at a specific location, the function needs to be continuous there. So this differs, or in contrast, when we're taking an integral, you can integrate a function even if it's not continuous. So here's just a very small example. So here's my y-axis and here's my x-axis. If I have a function, a piecewise function, let's say it looks something like that, I can integrate this function because essentially we're just finding the area underneath the curve. So from here to here, this would be this area, and then from here to here, we could calculate that area. Essentially, for this particular example, we're just summing the areas of two different rectangles. So notice that this function f of x is not continuous, and yet we are able to integrate it. In order to simplify the calculation of the integral, we often take the sample points to be the right endpoints, so then we can simplify the definition of the different integral to be: if f is integrable on the closed interval from a to b, then the definite integral from a to b of f of x dx is equal to the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I times delta x, where delta x is equal to b minus a over n, and x sub I is equal to a plus I times delta x. If the purpose is to find an approximation to an integral, it is better to use the midpoint of the interval instead of the right endpoint. Keep in mind that any Riemann sum is an approximation to a definite integral, but using the midpoint gives us a better approximation. And so here we have the midpoint rule in this purple box, and it says that the definite integral from a to b of f of x dx is approximately equal to the summation from I equals 1 to n of f of x sub I bar times delta x. And so if we expand that summation, we get these terms here, and delta x is still b minus a over n. The difference is now, because we're using the midpoint of a subinterval is the average of its two endpoints. So just quickly, if I were looking at the subinterval and it went from 5 to 10, then the midpoint between these x values would be 5 plus 10 over 2, which is 15 over 2, or 7.5. So this would be the midpoint for this particular subinterval. That was just a quick example. Example 1 says, express the limit as n approaches infinity of the summation from I equals 1 to n of cosine of x sub I over x sub I times delta x as a definite integral over the interval from pi to 2 pi. So this thing here is equal to the definite integral from a to b. Here pi is our a value and 2 pi is our b value. So we have the definite integral from pi to 2 pi of, instead of using x sub I, we're just going to change it to x. So we have cosine of x over x. And then what happens is, as delta x gets smaller and smaller and smaller, when we're taking the limit as n approaches infinity, we know from calculus 1 that delta x and dx are the same. And so this is our definite integral. Our next example says, consider the function f of x equals 3x minus x squared plus 2. Part A says, evaluate the Riemann sum taking the sample points to be the right endpoints over the interval from -2 to +2, and n equals 4. In other words, find r sub 4. All right, so we want to find r sub 4, and our function here is f of x equals 3x minus x squared plus 2. As a next step, let's go ahead and calculate delta x. So delta x is equal to b minus a over n. In this case, our b value is 2, our a value is -2, and then our our n value is 4. So 2 minus -2 is 4, and we get that our delta x is equal to 1. So x sub 0, or a, is equal to our left endpoint, which is -2, and then our next x value is going to be 1 more than that, since our width, or delta x, is equal to 1. So we have -1, x sub 2 is equal to 0, x sub 3 is equal to 1, and then x sub 4 is equal to 2. So those are all of the x values that we're looking at that are going to help us break up our interval. And now what we want to go ahead and do is we want to think about the width. So r sub 4, all the widths of our rectangles are going to be 1. And then if we're using right-hand endpoints, then the height of my first rectangle is going to be f of -1. The height of my next rectangle will be f of 0. My next rectangle will have a height of f of 1. And then my last rectangle will have a height of f of 2. So here's a visual representation of what's happening. We know that our left endpoint is here at -2, then our next x value is -1, 0, 1, and then 2. So here in the cyan color, or blue color, we have the graph of our function, which it's a quadratic. So we're looking at f of x equals, I'm going to reorder the terms, so we have -x squared plus 3x plus 2. So that's a downward facing parabola, and we want to estimate the area underneath the curve. So for my first rectangle on the right hand side, I'm going to create the height by using f of 2. And so if I do that, it stops there, and there is the height of my first rectangle. And then my next one is going to go here, and my next rectangle to the left, its height is dependent on x equals 0. So if I evaluate f of 0, it's going to give me that one. And then if I plugged in -1 into my function, it's going to give me a negative y value. And so that means that we're going underneath the x-axis. And so my rectangle is going to look like that. So I'm going to make a quick table. I have my x values and then my f of x values. So I'm plugging in 4 x values. I'm plugging in -1, 0, 1, and 2. If you want, you can pause the video and go ahead and evaluate those. So here are the y values. I went ahead and plugged those in, and you can also see them from the graph that we have to the right here, because we have a grid, so we can see the y values. So now if I am continuing on my calculation for r sub 4, we have r sub 4 is equal to 1 times f of -1 is -2, f of 0 is 2, f of 1 is 4, and f of 2 is also 4. Notice that I dropped the 1. Now I'm just going to go ahead and add those together. -2 plus 2 is 0, and then 4 plus 4 is 8. So we have that our right Riemann sum with 4 subintervals is equal to 8. And here's another way that you can see that. In our picture, each colored rectangle has an area of 1 because its width is 1. We know from x equals 0 to x equals 1, our width is 1. And then from here, it also has a height of 1. So each of these rectangles has an area of 1. So the green rectangles, we are thinking about those as being above the x-axis, so that's why they're green. And then the ones that are below the x-axis, they're red because we're going to subtract those off. So if I'm just individually counting these rectangles, since they all have an area of 1, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then I have 2 rectangles that are below the x-axis, so 10 minus 2 is what gives us 8. And so that's just another way to think of this particular example when we're calculating R4 and a visual way of thinking about it. All right, so part B says use the midpoint rule with n equals 4 to approximate the definite integral from -2 to +2 of the same function. In other words, we're finding m sub 4. So how does m sub 4 differ from r sub 4? Well, if I want to draw my rectangle, the way that I would have drawn it for r sub 4 on the very right-hand side would have been looking something like that. But Now what we're doing is, for this subinterval between 1 and 2, I want to use the midpoint. And so I'm going to think about the x value 1.5, which is the average of 1 and 2. And I want to think about where the y value is there. And I'm just approximating it here, so it looks something like that. And then for my next subinterval, between 0 and 1, I have 0.5, and the height of my rectangle is going to look something like that. And then between -1 and 0, I have -0.5. And so its height is going to be kind of low, and it looks something like that. And then for my last rectangle, I'm finding the midpoint between -2 and -1, which is -1.5. And then I'm going to drop that down, and it hits my graph about here. And so my last rectangle is going to look something like that. Okay, so let's do the actual calculation for m sub 4. Still, we calculated earlier that delta x is 1, so I have 1 representing the width of each of these rectangles. And then I want to figure out the heights. So I have f of -1.5 plus f of -0.5. And then our next height is f of 0.5. And then finally we have f of 1.5. So I'm going to go ahead and plug those values into our function and see what we get. All right, so I went ahead and I plugged those x values into our function, and I calculated and found that m sub 4 is equal to 3. And here is just a much nicer version of the visualization that I tried to draw earlier. Remember, the green rectangles represent the rectangles that are above the x-axis, and then the red ones are the ones that are below the x-axis. So we're taking all of the green area and then subtracting off the red area. And if we do that, we should get a value of 3.